So this is the title of my talk, although I decided I'd change a little bit the thrust of what I want to talk about. I do want to just remind people about two things. One, as Marco said last night, that the next year is the 10th anniversary of the founding of the VPH. But it's also, the end of this year is also the 500th anniversary of the birth of Vesalius. And I think that's an extremely important date for this community, because Vesalius is the father of anatomy. And I think we should look for ways of celebrating this event later on this year or next year. So I'm going to just add a little bit to the history that Marco briefly gave last night of the origins of the VPH, and extend it in terms of what we now call the VPH Physiome project, because the VPH started as a European initiative, but it does have antecedents with the Physiome project started by the International Union of Physiological Sciences, very much motivated by Dennis Noble and his probably in the 1990s, quite around. So in 1997, the IUPS, the International Union of Physiological Sciences, which is the umbrella body for all of the physiological societies, created the Physiome Committee, and I was asked to chair that, and we began immediately on the development of standards, because it was recognised by the physiology community that for modelling to have a major impact on the field of physiology, we needed to be developing robust standards for reproducible modelling. And about the same time, the systems biology community, the molecular systems biology community, recognised similarly the need for a common markup language, SBML. So those two efforts started about the same time, and are now increasingly, in fact, merging their efforts together. In 2003, the US government began the IMAG initiative, so that this was bringing together all the agencies funded by the US government that would have an interest in multi-scale modelling, and very much led by Grace Penn, who still is actively involved, and there's still an annual meeting of that multi-scale modelling group that meets around September, around this time, in fact, every year in Bethesda, to see how the NIH can, in particular, and these other agencies can promote the use of modelling standards. Then, as Marco said, in 2006, the step, or 2005, the VPH idea was launched, and then the development of a roadmap led by Marco as a strategy for the European Physiome under Framework 6, in fact, but kicking off the funding in Framework 7, and in particular the beginnings of the Network of Excellence, which started, and then that became essentially the work of that Network of Excellence was passed over to the VPH Institute to carry on the momentum that had been built through that Network of Excellence. But there's a couple of other important initiatives in there as well, and one is the IMI, which is another division of the European Commission, Innovative Medicines Initiatives, and that funded a few years ago the project called DD More, and that was an attempt to bring the pharmaceutical companies into the same standards-based frameworks, and that's also had quite a lot of overlap with the VPH. And then in 2010, the German government funded, through its MBNF program, funded a virtual liver network, which is headed by Adriano Henny, and that's coming to an end next year. Hopefully that will also carry on, but that's been another very important initiative in terms of building from molecular level scales up to whole organ scales, in this case the liver, and in this case particularly studying non-alcoholic fatty liver disease. So that's probably the most currently, alongside the cardiac work is probably the most advanced of the multi-scale modelling projects that go all the way from molecular function up to whole organ function, and increasingly with clinical goals for it. So I just want to thank Steve for this conference. This is not a very good photo I took yesterday, the night before rather, at the opening. And those of us who know him well, I think it's the first time we've ever seen him in a tie. So I just thought I'd let you know that this is the way we normally think of him, as a beekeeper or a farmer with an extremely sharp mind who continually challenges us to, in terms of the Physiome project and the VPH. And he's an anarchist, basically. As you saw with the title of the interface focus journal that he's wanting to pull together now as an outcome of this meeting, and he'll be sending an email shortly about this, but this concept of a necessary key to the creative destruction of medicine is a typical Steve challenge to the community, really. So, on that note, I also want to, this is another slide from Steve, and a very characteristic slide, I think, of his, which is a quote from Brown, are that means reach that exceeds grasp or what's heaven for. And I think that very nicely sums up the sort of aspirations that we should have for this VPH Physiome project. So what I'm going to do is to really use this talk to think about where the VPH is going, where it is at the moment in terms of why it exists as a particular organisation, and where it should, and try and get a little bit of discussion, if possible, at the end about where it should be heading. This is the third VPH conference. So why do we hold these conferences? Why? I mean, there's lots of bioengineering conferences around the world, lots of imaging conferences, lots of conferences specifically to do with particular organ systems. Why do we have these conferences? Why does the VPH Institute exist? I mean, there's plenty of organisations you would think with potentially related goals. Why should we have a particular organisation that's promoting the goals that we see for the VPH? And how do we differentiate ourselves from other communities? And what are we doing and where should we be going? What should we be doing differently? So these are important issues because the VPH had a high profile in the Framework 7. It's thanks to a lot of hard work led by Marco and others. It's also gaining a acknowledgement within Horizon 2020. But that does require continual reminding the politicians and the people in control of large science budgets and some of the scientists involved with that process of dispensing large science budgets, the importance of this integrative approach to physiology and its value for medicine. And I think we have to keep on challenging ourselves about what it is that's important in what we're doing if we're going to be able to successfully carry on the work and justify the funding. There's quite substantial funding that's going into this area, not only in Europe but also in other places around the world. We don't deserve this funding unless we're clear about what we are trying to achieve. So here's some thoughts, and this is really the basis for my lecture, is I want to talk about, first of all, what are the primary VPH challenges that are different from the way other groups see scientific challenges. I think, and these are my own biases in a way on what I think is important in this area, but standards and standard-based tools I think is an absolute key, and I'll talk more about why I think that is. Model and data sharing as a community, both through the model repositories and increasingly the use of atlases to make patient data with models available on a population basis. And I'll talk about a couple of those. And then I think it would be good to just briefly think about whether we should be doing more in relation to grand challenges and benchmark problems to focus this community on where we are heading. And then I want to just briefly also talk about model-driven medical devices, because I think as we move into modelling having a real impact on healthcare, it's going to increasingly be because those models are coupled to wearable, home-based, etc. medical devices. And we need to think through the whole pipeline of how the models get used, get coupled to devices, and how that impacts on the healthcare system as part of that scenario. And then I'm not going to talk about this one, but Bernard de Bono, who follows me and I've been working with, is really, I think, beginning to show the way for us in terms of addressing the tissue gap, the fact that we have these wonderful comprehensive databases of molecular knowledge, and we can put that together in terms of pathways, ion channels, gene regulation, metabolism, etc. And we've got, from the world of engineering in many ways, and physics, we've got the models and the technologies that allow us to do finite element or other numerical approaches to handling complex geometries and complex physical processes that interact at the organ level. I think we don't put nearly enough effort into thinking about how we really need to be dealing with the detailed structure of tissue, the organisation of cells within tissue, and how that can then link down to molecular biology. And I think Bern's talk will help us show a direction for that. Straight out the line. So what are the primary VPH challenges? I think we have to cope with multi-physics, multi-scale complexity of human biology. We have to really focus on reproducible models. I mean, science is all about reproducibility. So if you can't demonstrate the reproducibility of your results to a reviewer, then it's not really science, essentially. We have to develop the technologies and the standards and the methods in order to be able to demonstrate reproducibility by people that aren't involved in the original formulation of a model. And we have to be able to take modular approaches. It's so complex, we have to develop ways of modularizing. And that has to be based on, I think, on data and modeling standards. So there are 12 organ systems in the body, and there are now Physiome projects on all 12 organ systems, some of them more advanced than others, but people are collaborating all around the world on attempts to put together multi-physics, multi-scale models that deal with human biological function across all of these organ systems. And I think we're going to increasingly move into an age in the next 5 or 10 years where these models talk to each other for addressing disease issues. And again, there's something that some of the framework that Bernard will talk about is going to be highly relevant for. So we do need to be starting to think about how these mechanistic models, multi-scale models, can impact together with models of other organ systems, impact on particular diseases, on the diagnosis and treatment strategies for particular diseases. So just mentioning by way of illustrating the frameworks which are applied now across a number of organ systems, but the heart frameworks, which will be familiar to many people here, the fact that we're dealing with these scales that span spatial scales of 10 to the 9 at least, and temporal scales even greater, and that we're using the technologies of mathematical physics and engineering to be able to solve these equations at the organ level, but very much based on detailed knowledge of structure and developing the instrumentation to measure structure and model it at the tissue level. And then linked down to many lump parameter models at the cell level, but I think also increasingly potentially needing to deal with 3D architectures within cells. And every cell feels its mechanical environment. All signaling systems are interacting constantly with those mechanical environments. So we've got to be able to deal with the process of conducting forces all the way from extracellular tissue down to nuclear membranes and down to effects on chromosomes. So these are the sort of challenges we're facing, and typically at the organ level they involve all these types of physics. Typically at the cell level they involve these sorts of processes: calcium transport, mechanics, signaling, metabolic pathways, gene regulation. And very often we, the beginning point for many of them, of this type of modelling at the cell level, was the Hodgkin-Huxley equation. And I think there's a good question about whether we need to be much more addressing the 3D aspects of cell, and some people are, of 3D cell models. But also, I think as Joram will talk later on today, or later on this morning, the need to link these models, these rather over-parameterized models, for example, electrophysiology, encased in the Hodgkin-Huxley type approaches, or the equivalent markup extensions. We need to be linking those down to molecular dynamics. A very challenging problem, but one I think that you will hear more about today. So all of this depends on instrumentation, it depends on imaging across all of these scales, and I think we wouldn't be able to do a lot of this work without the tremendous advances that have been made in MRI technologies, micro-CT, and micro-CT now can image down to about the same resolution as confocal microscopy, 350 nanometers. And confocal microscopy itself is now pushed way down below that in the form of being able to specifically use markers that are highlighted for getting higher resolution where you can label the proteins. And then electron tomography for building 3D models of cells, and then X-ray diffraction and other technologies for getting protein structure. So equally, just as important as those modeling frameworks are now those imaging frameworks are now dependent on all the effort that goes into developing those imaging technologies. Likewise, we're benefiting from 150 years of effort by mathematical physicists into encapsulating the laws of nature into these beautiful equations that we all use and love. But we need to constantly remind ourselves, I think, where the biology comes into these equations, because to me these terms like for example, the diffusion constant in a reaction diffusion equation, or a current source term, or a stress strain relationship, or a viscosity in Navier-Stokes equations, or a permeability in Maxwell's equations. All of those terms are really regarded as empirical constant in the engineering world, but that's where all the biology comes in, because those are the terms where you have to delve into the multi-scale structure of the biology to understand how those terms change with growth, how they vary spatially. Think of this term here represents all the ion channel currents that come from membrane ion channel activity. This term here represents the detailed structure of an anisotropic, inhomogeneous structure of soft tissues, for example. And often, in order to formulate a constitutive equation such as this, we have to really understand the detailed components and the organization of those components within tissues in order to understand spatial variation and growth processes, and so on. The blood viscosity in Navier-Stokes depends on the rheological properties of blood, which can change very substantially from a biochemical point of view. So we need to be seeing these engineering constants as really little windows into a multi-scale biological hierarchy that we need to understand. So here's our challenge from pathways at the molecular level, where we have a huge amount of data, and we've got to assemble those into cells. There's only about 300 cell types, and if you look in detail at those cell types, in fact there's probably only 20 or 30 really distinct cell types. A lot of the others are variation, relatively minor variations. So we need to be understanding what is it that makes a particular type of cell special, how does it use those underlying pathways, how does it adapt to its environment. And this comes back to the tissue issue, because I think much of physiology is really addressed at the level of these what Bernard and I call secondary functional tissue units, where the organisation of typically only about 5 cell types in a 3-dimensional environment determines the function of a kidney, nephron, liver lobule, lymph node, immune system, osteon and bone, etc., acinus in the lungs for respiration. So, in many ways, the key understanding of physiological processes is really occurring at this scale, typically 100 or 200 microns of length, sometimes only 200-300 microns across in the other dimensions. So we should, I think, be putting a lot more effort into understanding how physiology works at this scale, because all that then happens is you scale it up with multiple generations of blood vessels. You have 1 million nephrons in the kidney, to roughly 1 million branching airways to bring you down to the alveolar gas exchange, and so on. And different mammal sizes are very much to do with just different levels of different numbers of generations of branching blood vessels to be able to multiply out. A mouse has essentially the same nephrons as an elephant. The difference is the elephant has a lot more nephrons, a lot more generations of blood vessels to connect them all together. So the key area where physiological function emerges, I think, is at that scale. But of course we have to link those units into whole organs and those organs into whole organ systems and address the environment in which we live and look at the interaction between that environment and the gene regulation and epigenetics. So the second point is standards. If we don't have standards, we can't do reproducible modelling. When we've begun with the development of the CellML and SBML efforts, and these are now fairly widely used, but at this website, cellml.org, and a similar one for the biomodels SBML group. But equally, we need to make sure that the tools we're building can have these application program interfaces that talk to those databases, so that people can be sharing models with common software platforms, and those models can be tested in all sorts of ways to make sure that they're consistent with the intention of the author. And there's very, very few models that are published without errors in them, so we need processes that can correct those errors and make these models both curated to make them accurate against the author's intention, but also annotate in a way that allows them to be combined and built through modules into more complex systems. So for CellML, the software environment that's being developed by Alan Garney, now assisted by David Brooks in Auckland, is using the CellML API and building a very sophisticated, open source, freely available environment at that website for across all platforms for doing cell modeling and being able to both author tools and also author models, curate, run, simulate, and combine modules to make more complex models. And with the mathematics always being encoded behind the scenes in these markup languages, CellML or SBML. We saw, a few years ago, we saw the need to have data standards, particularly for time-varying data, that would complement the model encoding standards. And Dave Brooks in Auckland has recently completed his PhD thesis on developing a standard called BioSignalML. And that is now being incorporated into Alan's OpenCOR architecture so that we can properly encode experimental data or modelling results into model repositories in a standardized form where we're dealing with all the metadata associated with some time-varying signal. And then an equally important part of all of this is the semantic annotation. Bernard will talk more about this, but the ability to build composite models depends on your ability to label the components of the model with standardized terms that the ontologists come up with. And there are typically 5 ontologies that are needed to do this for the type of world that we live in. So Chevy for chemical IDs, Go for cell components, cell type ontology, the foundation model of anatomy for the anatomy, and one of the ontologies that deals with physics, such as the biophysics. So you've got to annotate both against the biology and against the physical concept being represented by a particular mathematical term. So here's just a very brief look at where this is heading. Alan, the first two of these have now been done, in fact, in the latest release of OpenCOR, and Alan will be talking about this on Friday, maybe even today rather, is incorporating BioSignalML API into OpenCOR, putting a Python shell inside OpenCOR in order to open up a lot more, be able to make use of a lot more analysis tools as part of OpenCOR. Full CellML authoring will be there within about 3 to 6 months, and then the annotation is already there, but is depending on some work from US groups in terms of the composites, but that I think will also be there for support for SBML. So the SBML and CellML groups together have developed a markup language framework for encoding the simulation parameters and specifying exactly what the simulation is, and that's being incorporated into the tools, both SBML and CellML tools, including OpenCOR. I mean, we've already done quite a bit of work with stochastic modelling, and that will be more formally introduced through the CellML 1.2 release. David Nickerson in Auckland has been doing a lot of work with drag and drop modelling. That's going well. I think the ability to grab models from a repository of individual enzymes or ion channels or modules of any scale and drag and drop it into the working environment for model building, where because of the annotations it can automatically connect to what's in your current environment. So that's another aspect, I think, that is going to be an extremely important target for OpenCOR. And then the analysis tools. And I just wanted to talk about one of these analysis tools briefly, which in fact Harold Martins gave a talk yesterday on meta modelling, but we're trying to bring some of his ideas into the OpenCOR framework and into other modelling frameworks. So the way it works is that you have an experimental design, and Harold's going to have to forgive me for an oversimplified representation of ideas here, but the fact that you can appropriately design a set of input parameters and output parameters, and then you run a predictive model, a very expensive often calculation, but you can run it many, many times to fill out a state space description based on those input and output parameters. And then once you've captured that information about what the model does, its phenotype and its relationship to inputs, in state space, then you can fit, this is what the partial least squares regression process does, you can fit linear or piecewise linear or functions that then enable you to sample that state space very, very rapidly from either the output direction or the input direction. And that then means that you can start to compare with data. If you have data late that can be projected into that state space, then you can then look at the difference between the model predictions, and these meta models are now running thousands or million times faster than the original predictive model, but they're connected to the predictive model through an understanding of the sensitivity of parameters to the state space description. And then you can, on the basis of discrepancies between data and your predictive model, or your meta model based on the predictive model, you can begin to design new experiments and look for new mechanisms that are missing in the predictive models. And I think building these sort of tools into tools like OpenCOR and OpenCMISS and others that people are developing will just bring a lot of the power of these data-driven statistical approaches together with the power of predictive modeling in a way that I think is going to be extremely important in the future. So I just want to talk about model and data sharing. The biomodels database I've mentioned, the SBML database is contained in the Physiome Model Repository. But I also want to just briefly mention a couple of atlas projects, one cardiac and one skeletal that are beginning to build these model databases, but in conjunction with patient data across our population. So I think lots of people will be familiar with the Physiome Model Repository, which is shown here. This covers these lump parameter ordinary differential equations or algebraic equations across all of biological processes. It puts them into a robust form, reproducible, robust form that people can then download, and of course, you can spit them out in different languages. You can download the API as part of your building your own software tools, or you can simply copy and paste the code that's generated on the website for these CellML models. So I think it's also time to start thinking a little bit about where we're going with this CellML database. These are the categories of model at the moment, and I actually think we should be now thinking about how different communities can take responsibility for the development of some of these categories. An example would be the immune system. If we want to bring the power of modelling of immunology into connection with all sorts of other modelling that goes on in the body, we need to be making sure that the immune community, modelling community themselves, have some control and say in the development of these repositories of models to do with immunology. And the same goes across all the different other areas of biology. So I think one of the roles of VPH can be to try and encourage the engagement with these various communities in taking responsibility for model repositories and the encoding of models and putting them into these standard markup language form into the repository. And that would certainly help spread the burden of maintaining these repositories. I just wanted to give one example of the need for modularity. This is a cardiac example. We know a lot about cardiac ion channels. We have very good models. From the work of Dennis and Yoram Rudy and others, we have very good models of the electrophysiology of cardiac cells. And we also have the ability to understand the impact of proton transport, for example, and bicarbonate transport on those. And we can link those to models of excitation contraction coupling, very good models of calcium transport, and myofilament mechanics. But increasingly, we're now needing to regulate these models by signaling pathways such as beta-adrenergic pathways, which phosphorylate large numbers of proteins in these EC-coupled pathways mechanisms. So as this goes on, as we introduce more and more complexity here with different signaling modules that influence the primary electrical and mechanical and calcium processes that are underpinning the tissue organ level work, we need to be using these modular structures that CellML permits in order to make sure that we've got validation of these individual models experimentally, but then we've got a framework that can incorporate these modules into these more complex, depending on the question being asked, obviously, but into these more comprehensive models that need to deal with various timescales of signaling or growth, for example. So this is the other type of database of models of data that's currently being developed through various initiatives. So one of those initiatives is the Cardiac Atlas project led by Elizabeth Young in Auckland, called the CAP project, and that now has, I think, something like 5,000 human hearts in it with model fitted and other data associated with particular cardiac conditions. So these are fantastic databases for people to test models against and to understand the variability that exists in populations under various disease conditions. Another one is the Musculoskeletal Atlas project by Tor Bezier in Auckland, and this has funding from the FDA to build a database of musculoskeletal models that they then want to use for testing devices against virtual population. So the MAP project is another, in a sense it's copying the Cardiac Atlas project, but is aimed at producing large looking at particular bones such as the femur across a very wide population group, fitting models to them, and therefore being able to understand the phenotype of a particular organ, muscle, or a bone, or a joint, how that varies across the population, and how it changes with disease. So this is just a summary of these standards for models. We need the standards for experimental measurements, the minimum information standards that are a key part of underpinning those measurements, the data repositories such as Physionet, which can now be the BioSignalML standard has been run against the entire Physionet repository, and that makes it a lot more usable by the modelling tools. Other databases, the need for metadata and ontologies exists there, of course, as well. And then the access to all of that through application programming interfaces and web services. And then the similarly for the model standards, SBML, CellML, etc. And corresponding repositories, modules, and APIs and web services. And then the software tools, a variety of software tools that build on those, that have APIs that can then access models from those repositories. And then an important goal also, I think, with these codes and the use of these modelling standards is to have benchmarks. And Nick Smith, for example, in the EU HEART project, established a benchmark for testing electrophysiological cardiac models, and I think we need to do a lot more of that for different areas of computational physiology. The curation annotation process, I've talked about the need to use reference descriptions for models for the papers. The ability to give journals, the reviewing people, the reviewers of the journals, access to these models prior to publication so that they can check that the claims made in the paper match up with the model, and probably don't have to talk about that. So a lot of journals now do encourage people to deposit their models into repositories as part of the publishing process. So I just want to briefly talk about two other things. One is grand challenges. I think it could be that we need to be beginning to formulate grand challenges for specific areas of computational physiology that can be used with medical linkages to really challenge communities to compare their models against data. This has been done with two examples. One is the FDA NIH funded grand challenge on the knee, and groups, this has been going for a few years, and groups they'll put up a challenge of data, and groups have to develop their computational models to see if they can capture that phenotype. And similarly, the Cardiac Atlas project is another one that's now through the MICI conference it's been going for 5 years and has a challenge for you to be able to explain medical data through modelling. I think that's a good way to drive the community in different areas, but also for people to compare their models against other ones as part of the comparing against the data. And then finally, model-driven medical devices. I think we're increasingly moving into a world where the use of these models through mobile, through very sophisticated instruments that can make measurements that can be interpreted by models, can be miniaturized and coupled with lifting data up through cell phone networks to the cloud, coupled with personalized multi-scale models, and then linked through algorithms to the health and IT informatic frameworks. So this is a whole new world that I think the VPH needs to be involved in using our modelling frameworks to link to healthcare. And acknowledgements to, let's see, Rod's ready to kick me off. Acknowledgements to the CellML FieldML team in Auckland and Alan Garni in particular in France as well. A reminder that there's a couple of conferences coming up next year in New Zealand, in Auckland. One is the 10th Cardiac Physiome Workshop, which is April 8 to 10, and then immediately after CellML workshop being held on Waiheke Island. And these are some of the funding sources for the work that I'll talk about. Thanks very much. Thank you.
So I'm sure we all recognise that in Peter we have the opportunity to both stand on the shoulders of giants and stand with giants. On behalf of the organising committee, thanks very much. This is a book about Norway. So we're open for questions. Are there any questions for Peter?
Thank you for your fascinating lecture. In the beginning you stressed the need for modeling on the tissue level. So would you also say that we need new modeling paradigms there? Or are we okay in what we're doing right now?
No, I don't think we are. But I didn't want to talk too much about that because Bernard now is going to talk about exactly that. I think we do need new paradigms and new high data throughput approaches to gathering statistical information that can be used with models at the tissue level. But I don't want to steal Bernard's thunder.
Any more questions? I think I have a remark, which is that it seems to me that this section is really about infrastructure model standards. As we're going, I think we're seeing a need much more than we did 10 years ago. We were in isolated pockets and just did our specific levels. And now we need to learn how to share models better. I think we've been instrumental.
Well, I think as we've got to ask ourselves the question, why are we different as a community from a typical bioengineering conference? Why do we bother having a VPH Institute and a VPH conference series if we're not acting in a capacity to share data and models, build common tools, contribute to a community that is trying to do more than the sum of the parts? And otherwise we should just disappear into all the specialist areas that we're all contained in.
Great talk as always. I mean, I was just taking a bit of time to think about the CellML slides you put up towards the end with the lots of the list of anatomical subdivisions. And the point that you said that these really need to be picked up and curated, and the ownership for the anatomical subdivisions needs to be taken forward if it's going to survive, almost, if you will take it that way. Do you see the VPHI having a role in trying to bring that forward and take, in inverted commas, ownership of driving forward an initiative to take the anatomical subsections and bring it together as part of the VPH initiative in order to provide a home for coordinating and driving that forward?
Yes, I wouldn't call them anatomical subsections in that they're functional more, but yeah. But yes, I do think, there's no other group that can really take the overview needed to do this. So I certainly think the VPH Institute should help coordinate that effort.
Okay, so thank you, Peter. In the interest of time, we'll move on. Can we say thank you once again?